Good evening, Chesterfield. This is the end of everything. As you can see from the subtitle, we're talking about the fate of the Earth, the Sun, the galaxy, indeed all the galaxies, and the fate of the universe. So if you'll forgive me paraphrasing our friend Buzz, we're going to eternity and beyond. So I'll give a little bit of a prologue, and then we'll think about the future of the Earth, the Sun, the solar system, and then move into the far future and think about what's going to happen to stars and galaxies. And eventually we're going to think about the far, 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 far future and the ultimate fate of the universe. And so as not to leave you all thoroughly depressed at the end of the talk, I'll just give a slightly more upbeat epilogue at the end. So the story so far, in a different talk, I talk about how the universe began. We know that the universe is, at the moment, the observable universe is a sphere, some 100 billion light years across. But because the universe is expanding, we deduce that it all used to be a lot closer together. And if we wind the clock back far enough, we can say that, well, in the very early fraction of a second of the universe, everything that we currently see in a sphere 100 billion light years across used to be just centimeters apart. In other words, used to be contained within a cosmic golf ball. So I'm not going to go through the details because that's the other talk, but from this cosmic golf ball we ended up with the universe we see today. And the question is, where does it go from here into the future? In order to try and keep track of where we are in terms of how far into the future we're looking, I'm going to use these numbers along the top of the screen here. Each small box represents 10 times further into the future than the previous. So we can think about 10 to the power 3, 1,000 years into the future, 10 to the power 4, 5, 6, a million years into the future, and so on. 10 to the 9, a billion years, 10 to the 12, a trillion years into the future. And that red box is going to move from left to right across the top of the screen, and that will help us keep track of where we are in terms of how far into the future we're talking. And I'm indebted to the work of Adams and Laughlin, who wrote a paper about 25 years ago in which they laid out the timescales on which various astrophysical phenomena are likely to occur, and I've used their paper to try and get my slides in the right order. So I'm not going to talk about the next 10, 100, 1,000 years. I'm going to jump to 10 to the 4 because, well, we don't know whether we're going to have nuclear war, whether we're going to extinguish ourselves. Let's assume the human race isn't quite that stupid and we're going to continue for a long time into the future. But on a timescale of 10 to the 4 years into the future, we know things are going to change. Because the Earth's axis traces out a circle on the sky, this precession on a timescale of 26,000 years is the period by which the Earth's axis traces out a circle. So at the moment, the Earth's axis is pointing close to the star Polaris, but in another half cycle, in other words, in another 10 to 12,000 years, the Earth's axis will be pointing closer to a point near Vega. So Vega will become the new pole star. That's going to make it very easy for Boy Scouts to point out which way is north. Compared to finding Polaris, Vega is 5 or 6 times brighter, so it's going to be a lot easier for them. But there is a consequence of the pole star changing. At the moment, on the left-hand side, we can see that we're nearer to the Sun, perihelion, in January, which is during northern winter. But if the Earth's axis was pointing the other way, so it's pointing towards Vega, then we'll be nearer to the Sun during northern summer. So instead of the seasons being mitigated by that effect, they're going to be exacerbated. And any variations in the Earth's climate, which are due to the Earth's spin or the Earth's orbit around the Sun, collectively any such changes in the Earth's climate are called Milankovitch cycles. And we'll hear more of that in just a moment. On a timescale of 10 to the 5 years into the future, the Voyager spacecraft that were launched in the 1970s and went on a visit to Jupiter and then Saturn, and for Voyager 2, Jupiter, Saturn, and then Uranus and Neptune, they have both now left the solar system. And they're heading off in the direction of various star systems, and they'll pass through star systems on this sort of timescale, 10 to the 4 to 10 to the 5 years into the future. At the top of this diagram, Voyager 1 is heading off in the direction of the star system Gliese 445. And at the bottom of the picture, Voyager 2 is heading off in the direction of Ross 248. Pioneers 10 and 11 were launched a little bit earlier, but they're travelling more slowly than the Voyagers, and so they'll take a little while, but on a similar time scale, they will head out of the solar system and pass nearby stars. Pioneer 10 on the right there is heading off in the direction of Aldebaran, and Pioneer 11 on the left is heading in the opposite direction, sort of towards the centre of the Milky Way. And it's this sort of timescale that we can expect them to pass through lots of star systems. So in 1 million years, these will have passed through a few, if not a few dozen, different star systems. Still on a timescale of 10 to the 5 years into the future, we know ice ages are going to come and go. Historical records tell us that ice ages visit the Earth every 100,000 years or so. And the Earth entered a so-called interglacial period, a warm period in between ice ages, relatively recently. And so we know that the next ice age is due on a timescale of about 10 to the 5 years. And this is another manifestation of a Milankovitch cycle, because it's due to changes in the way the Earth orbits the Sun. Still on a timescale of 10 to the 5 years into the future, we know the Earth is going to continue to slow down. It's been slowing down for decades. Rather unusually, it appears to have been speeding up for the last few years, for reasons we don't quite understand. But we know that the tidal effects of the moon tugging on the Earth are slowing the Earth down. In effect, the moon is robbing the Earth of some of its angular momentum, and so the spin of the Earth is slowing down and the moon is moving to a larger orbit. In past year, we've added a leap second every once in a while to keep our watches and our clocks synchronized with the rotation of the Earth. We've added a leap second perhaps once every few years. But as the Earth continues to slow down, by the time we get to this point, 10 to the 5 years into the future, we'll need to add a leap second perhaps every day, not once every few years. In other words, the length of the day will at this point be about 24 hours and a second, rather than 24 hours. Still on a timescale of 10 to the 5 or thereabouts, we would expect some stars to go supernova. It's very difficult to predict exactly when, but Eta Carinae in the southern hemisphere is definitely a candidate for going supernova. For the last few thousand years, it's been sloughing off some of its outer atmosphere, and that's been producing the nebula that we can now image, for instance here imaged with the Hubble Space Telescope and an astronomy picture of the day a few years back. So we know this star is very massive, and we know it's quite unstable, which is why we think it's a candidate for supernova. We can't say when, but it's likely to go off before 10 to the 5 years into the future. It might be beaten to the punch by Betelgeuse in the northern hemisphere. Here's an astrophotographer showing what Orion looks like, in which Betelgeuse has been artificially brightened to show what it might look like when it eventually goes supernova. It's likely not only to be a very bright object in the night sky, but hopefully a very bright object during daylight hours when it does decide to go. But it's not only supernova that we have to think about. Those stars are distant enough from us that they're probably not going to be a threat. But another possible threat to Earth is a gamma-ray burst. For instance, stars like this one, Wolf-Rayet 104, this is simply an artist's impression. These stars, none of them are particularly close. This one happens to be 7,000 light years away. If that's 10 times further away than Betelgeuse, that might seem that it ought to be quite safe. But actually its death might result in a radiation burst even more powerful than a supernova, because these systems have very rapid rotation and, by a mechanism that we don't fully understand, often produce jets. And when they die, they can produce a great deal of gamma radiation along those jets. So if the jet happens to be pointing towards Earth when it dies, then that could be a serious threat to life on Earth. But it's rather difficult to tell exactly which direction those jets are pointing. On a timescale of 10 to the 6 years into the future, now we're talking 1 million years from now, We know that various stars are going round the centre of the Milky Way in various orbits. The Gaia spacecraft has been mapping out star positions very accurately, and so we've come to the conclusion that we are moving around the Sun, and lots of stars in our neighbourhood are independently moving in orbits, which means that because they're not all identical orbits and they're not all circular, sometimes some of our neighbouring stars will drift closer to us and then away again. And it's been calculated from these motions that the star Gliese 710 is going to pass close to us in 1 million years or so. So close that it will actually enter our Oort cloud, the cloud of icy particles that are gravitationally bound to the Sun. And when this star enters the Oort cloud, it's going to disrupt a lot of these particles, and a number of them are going to come raining down into the inner solar system, producing, it's calculated, many interesting, bright, naked eye comets, perhaps one a month for millions of years. It's interesting to note that at this point, when Gliese 710 enters our solar system for a short while will actually have 2 suns, just like other places we know and love. Still on a timescale of 1 million years into the future, this is Meteor Crater. Am I showing this image because it's likely to get an impact like that every 1 million years? No. This image is shown, well, reason number 1 is so that we can appreciate what a stroke of luck it was that this impact just missed the visitors centre. Wow, yeah, that was a close call. But no, the reason I'm showing this is because on a timescale of 1 million years, we can expect impacts like this to be eroded due to weathering. So any impact similar to this size that's more than 1 million years old, it's quite possible we wouldn't even notice it. Whereas more recent ones, this one is perhaps only a few tens of thousands of years old, we would still see it. Now, weathering is something that we understand in the Earth's atmosphere, and you might say, well, in that case, we would expect craters on the moon to last forever because there's no weathering there. Well, not strictly true, no weathering in the conventional sense, but the moon is being constantly bombarded with micrometeorites, and that effectively pulverizes the surface. So Aldrin's footprint here is not going to last forever. The micrometeorites will eventually erase any trace of the Apollo landings. Indeed, any trace of the Apollo hardware will eventually be erased due to these micrometeorites, a form of weathering that's not weathering as such, but due to the changes on the surface of the moon. Moving forward to 10 to the 7 years into the future, the plaque that is sitting on the side of Pioneers 10 and 11 will eventually become unreadable. The interstellar medium is not empty, it's not a perfect vacuum, it's full of some gas and also some dust particles, tiny particles of perhaps carbon or silicon materials. They might only be a micron or so in size, but after a few million years of travelling through the interstellar medium, the plaque is going to be pitted and eroded and will become unreadable. So if any of the civilizations that I mentioned earlier, when Pioneer and Voyager are travelling through other star systems on timescales of perhaps 10 to the 5 years or so, if Pioneer has passed through hundreds of these star systems, anybody that picks up Pioneer will be able to look at this plaque and be able to read the pulsar map on the left and get an idea of the size of the humans that sent it and the fact that it came from the third rock from the Sun in our particular star system. But if it's not picked up in a few million years, if it's picked up in 1 billion years or so, then it might be that the Pioneer spacecraft itself still survives, but anybody who picks it up will not be able to read the plaque and so will not know where the Pioneer spacecraft came from. 10 to the 8 years into the future, we can ask what's going to happen to Saturn's rings. We can ask ourselves first, before we say what's going to happen in the future, well, do we understand where they came from in the first place? Is it possible that a moon, such as a moon the size of Mimas, if we take that amount of material, is it possible that that amount of material, if a moon was disrupted by crashing into another moon or a comet struck it or something like that, if we destroy a moon and let the dust settle, will we end up with something like Saturn's rings? When we see a moon like Mimas there shown in the photo, we can say to ourselves,
"That's no moon. It's a space station."
Because it does indeed bear a certain resemblance to the Death Star from Star Wars. But a simulation has been done by starting with, let's assume we have Saturn and let's ignore all the other moons except one, which is about the size of Mimas. Let's smash it up. Let's just imagine it disintegrates instantly. Let's imagine that it could have been hit by a comet or something like that. What would then happen to all the debris from this moon? You might assume that the debris would simply keep on orbiting Saturn with the same period as the original moon. But the simulations actually show that the debris starts to stretch out into the orbit, and look how fast it happens. In the bottom right there, it's only a matter of days before the debris ends up occupying the entire orbit of the original moon. That's simply because all of the tiny particles, all of the tiny debris that was left when the moon disintegrated or was pulverized, they all interact with each other, they're all banging into each other, and hence they're slowly distributing themselves around the ring system. If that's how the ring system came to be, then all of these particles will have been slowly spiraling inwards, and so over millions of years the debris would eventually produce the ring system that we see today. But that process hasn't finished, it's ongoing. So all of the individual particles in Saturn's rings, as well as being shepherded by the various moons that exist, are all spiraling inwards. And anything on the inner edge of Saturn's rings is raining down onto the surface of Saturn. And it's been calculated that on timescales of 10 to the 8 years into the future, that process will result in essentially all of Saturn's rings simply raining down onto the surface, and there will be no rings left. So all of you who like to look through a telescope at Saturn's rings, get in now, because in another 100 million years it will simply not be an option. And perhaps we should remind ourselves that on this same timescale of 100 million years or so, the entire solar system is chaotic. So although we think of the solar system either shown by an orrery on the left or a tellurian on the right, showing the motion of the moon and the earth and the sun, we tend to think of the motion of objects in the solar system as being clockwork. We should remind ourselves that on this timescale, the solar system is chaotic. We cannot predict where things are going to be on these timescales. We can say with some certainty where Jupiter is going to be in 1,000 years or 10,000 years or perhaps even 100,000 years into the future, but not 100 million years into the future. Not only do we not know where the planets are going to be in their orbits, we don't even know how many planets there are going to be in our solar system. It could be that on this timescale, Jupiter decides, being the bully that it is, to eject one of the smaller planets out of the solar system. It could happen. We know there have been solar system readjustments and rearrangements and reconfigurations in the early days of the solar system. Perhaps that could happen in the future. Still on 10 to the 8 years into the future, now thinking of things on a galactic scale, we know that we rotate around the centre of the Milky Way on this sort of time scale. There's us in between two spiral arms, two of the major spiral arms of the Milky Way. So at the moment we know we're sitting in between spiral arms in a relatively low density region. But it's been calculated that on this sort of timescale, 10 to the 8 years into the future, we are going to move into one of the spiral arms. In other words, we are going to be in a region in which we have a much higher density of stars around us. We're going to have many more stellar neighbours within a few light years of us compared to how many we have now. What are the consequences of having more stellar neighbours? Well, there are two principal consequences. One we've sort of already mentioned. If we have more neighbours, we have more likely incidents where a star gets quite close to us and disrupts the Oort cloud and results in us getting pummeled with rocks from the Oort cloud. If we have a look at how often species have been exterminated on Earth according to the record, we can see these spikes indicating it's happened quite a few times over the last few 100 million years. The last one on the right-hand side, the so-called KT boundary, the boundary between the Cretaceous and the Tertiary eras, that's the impact that killed the dinosaurs ultimately. So it's happened quite a few times, and it's speculated that perhaps when we are in a spiral arm of the galaxy, it is more likely to happen. So on this sort of timescale, here's of course just an artist's impression, but on this sort of timescale, a big rock could be coming our way. If you have a look at the left-hand side there, it looks like it's on its way to thump Italy. Okay, bad news for Italy, but of course if the rock is big enough, it is going to be bad news for the entire planet. Species will be exterminated if the rock is big enough. The only real question is, will one of those species be us? We've got a little bit of time to try and figure out what to do with large rocks coming our way if we've got another 100 million years to worry about it. But the second consequence of having lots of neighbours is that one of those neighbours might be a massive star which could go supernova. At the moment, there are no supernova candidates close to us. Betelgeuse is at 600 light years, for instance. But we think that if a supernova within 100 light years goes off, well, that could be a danger to Earth. And again, it's been calculated that if supernova goes off within 20 light years of Earth, that could, in principle, produce enough radiation to end all life on Earth. And if that sounds a little bit sensational, bear in mind that we know that we have had supernova candidates, supernova stars go off relatively close to Earth in the past. Any supernova within about 100 light years would leave a deposit of an isotope called iron-60 in Earth's sediments. To the best of our knowledge, iron-60 is an isotope that is only generated in supernova, and there's no other way that they can be generated and deposited in Earth's sediments. We know that iron-60 decays or changes into other elements, so it might start off as iron-60, but after millions of years it changes into cobalt and then into nickel. So if after a few million years iron-60 decays into nickel, and yet we find iron-60 in Earth's sediments, then we can deduce not only that they came from a supernova relatively close, because if it was a very distant supernova, it wouldn't have produced enough to be embedded in Earth's sediments, but we can also deduce that it must have gone off relatively recently. It can't have gone off many, many billions of years ago, and it can't have been around, this iron-60 can't have been around since the Earth was made, because iron-60 simply has a half-life that is too short. So there's evidence that supernova have gone off relatively close to us in the past, so it's no surprise that there is a possibility that it will do again in the future. 10 to the 8 years into the future, all of this time the Earth has been slowing down because of the tidal friction, the moon raising tides on the Earth, and so the moon will be robbing the Earth of some of its angular momentum, slowing down the spin of the Earth and increasing the size of the moon's orbit. The length of the day, it's calculated, will now be about 25 hours. It's pointless to start thinking about how many leap seconds would we have to add. That's just ridiculous. We would have to change our clocks. Perhaps this would be a good time to decimalize the clocks and say the length of the day is now 100 quarter-hour periods or something like that. The distance from the Earth to the Moon will have grown during these 100 million years, and at this point the distance to the Moon will be so large that there will be no more solar eclipses visible from the surface of the Earth. At the moment, the distance to the Moon is such that the disk of the Moon can just about cover the disk of the Sun. But in the future, when the Moon is further away, then that will no longer be possible. We can still have partial eclipses, and we can still have annular eclipses in which the Moon is lined up with the Sun but doesn't cover the whole disk of the Sun and leaves us with a ring of fire around the outer edge. But perhaps more importantly, rather than being disappointing for any photographers that want to photograph solar eclipses, if you're interested, get in now, don't wait for a billion years. A second consequence of the Moon moving further away from the Earth is that the Moon has a stabilizing influence on the tilt or the obliquity. the tilt of the Earth, about 23.5 degrees, hasn't changed by more than about a degree according to the historical records. That's because the angular momentum of the Moon is coupled with the angular momentum of the Earth, and they tend to stay locked together. But if the Moon is further away, perhaps 25% further away is all you would need for the tilt of the Earth no longer to be locked by the Moon. And then if the tilt of the Earth can vary, for instance, it could go from 23 degrees to 0 or possibly even to 90, the tilt could change erratically and hence result in wild changes to the Earth's climate. And that could be far more serious than the fact that photographers wouldn't be able to photograph total eclipses of the sun anymore. What's happening to the Voyager gold disk? On the Voyager spacecraft, there's a gold disk, a phonograph as indicated on the right-hand side. Remember, I said that the Pioneer disks would become, or the plaques would become unreadable on timescales of a few million years because of the impact of the interstellar medium dust. Well, it's thought that the Voyager gold disks will last a lot longer, perhaps 1 billion years or so. That means that if they do pass through solar systems once every 10 or 100,000 years, then the Voyager disks will have a chance of flying through thousands of different solar systems, and if it's picked up in any of those solar systems, then any intelligence will pick up the Voyager spacecraft, realize there's a disk attached, and perhaps then listen to the sounds of Earth and the music that's recorded on the disk, which is shown on the right-hand side. One of the reasons the gold disk will last longer than the Pioneer plaque is that the gold disk on Voyager is protected by a cover, as shown on the left-hand side. And it's the cover that's going to get pitted and eroded. It's a bit of a shame because it's the cover on the left that contains the instructions for how to read the phonograph on the right. So that's what these various scratchings are here. Not only a pulsar map saying this is where Voyager came from, but here's the instructions that tell you how to spin the disk and put a stylus in the disk, spin the disk at the right speed, and then you'll hear noises which correspond to greetings from Earth and music from Earth. So after 1 billion years or so, again, anybody picking up the Voyager spacecraft will not be able to tell where it came from and will not hear the greetings. Still on a timescale of 1 billion years into the future, the Sun isn't yet a red giant, but it is changing. On the timescales of billions of years, the Sun's luminosity will slowly increase as it evolves and moves towards its red giant phase. It's been calculated that the luminosity of the Sun will grow by something like 10% every billion years for quite a few billion years. And that increase in luminosity will be enough to drive the surface of the Earth to a temperature of about 80 Celsius. The oceans are going to boil dry and there's nowhere we can go. Going underground is not going to help in terms of this heat. We're going to have to leave Earth for a while and perhaps come back when it's cooled down a little bit. But the Sun is going to expand into a red giant phase. And it's been calculated that if you work out how large the Sun is going to become, its radius is going to be very similar to the Earth's orbital radius. So it looks like the surface of the Sun is going to get rather close to the Earth. And you think, well, this could be a problem. Is the Earth going to survive? Is it going to get engulfed by the Sun when the Sun expands to a red giant? Well, some astrophysicists say yes, and some astrophysicists say no. The jury is still out. And that's because as the Sun expands in its red giant phase, there will be very strong solar winds. In other words, there'll be a lot of mass of the Sun being lost into the solar wind. And if the Sun loses mass, then there's less gravity pulling the Earth, and so the Earth's orbit is going to expand. So this cartoon on the left shows what might happen. As the Sun grows and starts to expand, the Earth is actually going to move into an orbit which takes it further away from the Sun. So yes, the Sun is going to eventually engulf the original Earth orbit, but by the time that happens, the Earth will be in a new orbit, perhaps somewhere out where Mars is now. So it's possible the Earth might survive. The jury is out. Let's assume the Earth survives for the sake of argument. The Sun, having been through its red giant phase, now becomes a white dwarf, effectively the core of the Sun, after the outer part of the Sun has been sloughed off to produce what I'm sure would be a very nice planetary nebula seen from beyond the solar system. The outer atmosphere becomes a planetary nebula. What's left, the core of the star, is a white dwarf, possibly containing a large amount of carbon at its core. But one problem is not going to be the radiation from this star. One problem is going to be the fact that the Earth is going to lose its magnetic field at about this time. The Earth has a magnetic field because it has a molten core, and the core is molten not because of any heat from the Sun, but because of radioactive decay of elements producing particles which have energy which keep the core molten. And a molten core which is spinning generates a magnetic field by a dynamo effect. But eventually the radioactive decay of those elements, because they have a half-life of perhaps a few billion years, eventually there won't be enough energy from that radioactive decay to keep the core molten. Once the core of the Earth solidifies, it loses its magnetic field, and then we'll be exposed to radiation, perhaps not so much from the Sun, which is now a white dwarf, but from cosmic rays. That could well be a problem. It's been hypothesized that maybe this is what happened to Mars. Mars is a lot smaller than the Earth, and maybe its core cooled faster than our core did, and its core solidified perhaps a long, long time ago. And so if Mars lost its magnetic field a long time ago, then probably it lost its atmosphere a long time ago. It's left with a very small atmosphere, a very low pressure atmosphere, perhaps 1% of ours. Maybe it had a much thicker atmosphere, but that was lost at the point when it lost its magnetic field. And bad luck comes in threes. If we survive the Sun going through its red giant phase, if we survive the loss of a magnetic field, then we have another problem to deal with. And that is the Andromeda galaxy is probably going to come crashing into the Milky Way. People are still doing calculations to work out if it is going to be a head-on collision or a glancing blow. So for those of you who like taking pictures of Andromeda with a telephoto lens or a telescope, well, wait a little while and you'll be able to take pictures of the Andromeda galaxy with a wide-angle lens, because it's going to fill our sky as it comes hurtling towards us in a few billion years. As the two galaxies pass through each other, it's quite likely that no stars are going to collide with each other, but the gas and the dust is going to get so mixed up there's going to be a riot of new star formation as the two galaxies pass through each other. And then one galaxy will pass through each other completely, and then they'll eventually settle down after a few billion years. And it might look a little bit like an elliptical galaxy. I would imagine we'll lose the spiral arms of the Milky Way and Andromeda, and we're left with a glow in the sky as seen from Earth, in which we might have a nucleus from the Andromeda galaxy and a nucleus from the Milky Way. So perhaps there's still a supermassive black hole at each of these points, which used to be the center of the two galaxies. Those two supermassive black holes will orbit each other for probably quite a few billion years before they eventually merge together. On a timescale of 10 to the 11 years into the future, the slow dance between the Moon and the Earth finally comes to an end. The Moon has been slowing down the Earth and moving to a larger orbit. After 10 to the 11 years or so, one day is the same as 1 month. In other words, the length of time it takes the Earth to spin once on its axis would be the same as the length of time it takes the Moon to go around the Earth. So, in other words, the Earth will be tidally locked to the Moon. One side of the Earth will always face the Moon, much the same way as the Moon has always been facing the Earth. That's been a tidal locking of the Moon that's been with us for many billions of years. But at this point into the future, we'll also have tidal locking of the Earth. So Earth and Moon will both face each other, and those directions, the faces, will not change. So as always, standing on the surface of the Moon, you always see the Earth in the same part of the sky, but now it'll be true in the opposite sense. Standing at a particular point on the Earth's surface, the moon will always be in the same position in the sky. If you go to the wrong side of the Earth, the moon will simply never rise. And this picture, by the way, although it looks like a photoshopped picture, is a genuine picture taken from deep space. The reason it looks odd is because we have a full Earth and a full moon, roughly to scale at this distance, but of course we are looking at the far side of the moon, not the more familiar near side of the moon. So this is a genuine picture of Earth and moon as seen from a vantage point some distance away. What's happening locally on a timescale of 10 to the 12 years into the future, 1 trillion years into the future? We know that the Milky Way is surrounded by lots of small satellite galaxies. Many dozens, possibly even 100 or more small galaxies surround the Milky Way. And we've just said that the Milky Way and the Andromeda galaxy M31 are going to merge, and eventually the same will be true of M33, and indeed every small satellite galaxy of the Milky Way or Andromeda or any of the galaxies in the local group, this gravitationally bound region close to us, all of those are going to merge into one mega galaxy. Not actually a spiral galaxy as indicated by this icon, but probably a large amorphous elliptical galaxy. If that's going to happen on the immediate local scale, what's going to happen to more distant galaxies on this timescale of 1 trillion years into the future? During a lockdown challenge, I decided to try and image a very distant galaxy, and I was successful in imaging, even without a telescope, a very distant galaxy that's receding from us at twice the speed of light. In other words, at the moment, the universe is expanding at such a rate that a number of galaxies are relatively close to us, but even the very distant galaxies receding from us at greater than the speed of light, they can still be imaged because of the current expansion of the galaxies. And on the right-hand side there's a picture taken by the Hubble. This is one of the Hubble deep fields, the Hubble ultra deep field, a very small section of sky in which we're seeing thousands of galaxies. Some of those galaxies might be relatively close, but a great deal of them, especially the small dots, are at considerable distance, such that, again, many of these galaxies will be receding from us faster than the speed of light. And yet it is still possible to image many billions, if not perhaps ultimately, if we were to cover the entire sky, perhaps more than 1 trillion galaxies. But it's sobering to realise that in the future, a civilization that builds themselves a Hubble telescope and looks out into the universe to ask themselves what's out there, they will see nothing other than the stars in their own galaxy. In other words, all of these distant galaxies, which at the moment we can see, in 10 to the 12 years, the expansion of the universe will have taken them so far away from us, receding at such high velocities, that it will never be possible to see those galaxies. The light simply cannot reach them or reach us. So it's sobering to realize that a civilization that comes into existence on this sort of timescale in the future, when asking themselves what is the nature of the universe, what's out there, they will come to the conclusion that the entire universe is simply their own galaxy, and they will not be aware of the existence of other galaxies. Nothing to do with their technology, simply that the expansion of the universe will be such that all of these distant galaxies will be simply too far away. In the beginning of everything, I describe how all of the hydrogen in the universe was made. And it takes about 3 minutes to make all of the hydrogen in the universe. This is all of the hydrogen that ever since the birth of the universe has been used to fuel stars. But here we're talking 1 trillion years into the future. And although it only took 3 minutes to make all the hydrogen, after a few trillion years, it's starting to run out. So what are the consequences? Well, as a little bit of an aside, some astrophysicists say, well, maybe we can make stars out of something else. We don't need hydrogen. Maybe we can make stars out of heavier elements. What if we start with gas with much greater, heavier elements rather than starting with the lightest of gas, hydrogen? Maybe it's possible to make stars in which we have nuclear reactions occurring at the core, but perhaps if they're made of heavy elements, perhaps the surface temperatures could be low enough, even lower than, for instance, a red giant, which might have a surface temperature of just a few thousand Kelvin. Maybe you can have a star with a surface temperature of just a few hundred Kelvin. Is it possible to make stars with nuclear reactions at the core, but ice in the atmosphere? Is it possible to make frozen stars? Yeah, okay, that's the Disney version of frozen stars. Okay, that's not what I'm talking about. If that's the picture you've got in your head, then let it go. Because what I'm talking about is stars, nuclear reactions at the core, but ice in the atmosphere. Some astrophysicists say this is possible. Other astrophysicists say, no way. You absolutely need hydrogen to make stars. You can't make stars out of anything else. And so in order to understand what happens next, we need to think about, well, what's happening on the largest scales of the universe in terms of how the universe is evolving. And here's an indication of our understanding at the moment. This is a graph of the relative size of the universe on the vertical axis as a function of time. And there are 4 coloured lines. And the question is, which coloured line are we on, or which one represents our universe? So that's where we are now with a relative size of 1. But you can see the age of the universe. When did the Big Bang happen? Well, it depends on which of those coloured lines we are currently on. And each of the coloured lines represents a universe with a different amount of mass or energy in it. So if we can determine what is the mass of the universe, what is the energy in the universe, then we can figure out which of those coloured lines we're on. So for instance, if there was a great deal of matter in the universe, then gravity would be able to pull that matter together, and we would be on the orange line, which means the universe would expand for a while, but eventually would come back and we'd end up with a universe of size 0, because we would end up in a big crunch because gravity would win and we'd be in a closed universe. When I was young, scientists seemed to be fairly convinced we were on the green line. In other words, it was going to expand, and it would expand more and more and more slowly, and the gradient of the green line would eventually plateau out to level. But actually, we don't think we're on the green line anymore. The latest evidence from the last couple of decades is that we're on the red line. With the amount of matter and energy in the universe, we think not only we're in an expanding universe, but look at the gradient of the red line. The expansion is getting faster and faster and faster. We're in an expansion phase which is accelerating. This was a bit of a surprise as of a couple of decades ago, but that is our best estimate as to what's actually going on. That gives us a Big Bang of 13.8 billion years ago, and the red line tells us what's happening in the future. So there's no sign that the universe is going to contract and eventually go back to 0. It's going to continue expanding. Okay, if it's going to continue expanding, I need to change the numbers at the top of the screen so as not to be here for the rest of the week, basically. So each small box in the timeline above now represents 1,000,000 times further into the future than the previous box, not just 10 times further into the future. And I don't know what adjectives we're going to use. Is that a zillion years, a gazillion years? I don't know what names we're going to give these things. So we'll just stick to 10 to the power very large numbers for the future. So where did we end up before we took this little aside to say how is the universe expanding? Well, we said it took 3 minutes to make all of the hydrogen in the universe. We don't think we can make stars out of anything other than hydrogen. But after a few trillion years, the hydrogen is starting to run out. Now, big stars don't last very long. Small mass stars can live an awful long time, not just a few billion years, but low mass stars might live for trillions and trillions and trillions of years. But they don't last forever. No star lives forever. So if the hydrogen is running out, what does that mean? There will come a time when there are no more stars shining. The age of starlight will come to an end. The stars themselves, whatever's left of them, will continue to orbit for a while. Dead stars such as white dwarfs, neutron stars and black holes. It might seem a bit odd to talk about white dwarfs not shining. Surely they're white. Doesn't that mean they shine? Well, yes and no. There's no nuclear reactions to keep them hot. So although they are born like the one that will be eventually from our sun, when our sun dies it will generate a white dwarf, but it's only hot because it was born hot. There's no nuclear reactions to keep it shining. So it basically will cool down relatively quickly and it will become a black dwarf. So none of these objects will be shining in the conventional sense. Some stars will be ejected from the galaxy and some will be eaten by the central supermassive black hole, SMBH, from here onwards. We have evidence by looking at other galaxies that the magnetic fields present in the galaxy will funnel material into the supermassive black hole in the centre. It's difficult to see what's going on in our galaxy, but for instance, SOFIA has mapped out magnetic fields in other galaxies. SOFIA is the Stratospheric Observatory for Infrared Astronomy, the 747 with an infrared telescope in the back, and that's mapped out magnetic fields as shown on the left. And we think those magnetic fields will effectively funnel material, including some stars, into the supermassive black hole at the centre of what we believe is every galaxy. What's going on with all of the atoms in the universe? Well, there aren't any atoms in black holes, there aren't any atoms in neutron stars, but there are still some atoms in what's left of the white dwarfs, or now black dwarfs. Atoms are positively charged nuclei surrounded by negatively charged electrons, and protons are responsible for that positive charge. The protons may or may not change or decay into something else. If they do decay, if they do change, then all atoms in the universe will fall apart. We don't really know the timescale on which that will happen. We don't know if it will happen, and we don't know the timescale if it does. It's unlikely to happen on a timescale less than 10 to the 36 years into the future. But in a sense, it doesn't really matter whether all the atoms fall apart or not, because the only atoms are in black dwarfs. And even if protons don't decay, the atoms will survive for a little longer, but eventually even black dwarfs will evaporate and just leave radiation, and hence leave no atoms in the universe. That's an effect of quantum mechanics, which I'm not going to go into. What's going to happen to the black holes? Well, remember, when galaxies merge, the black holes at the centres will merge. So any galaxy in a cluster of galaxies that's gravitationally bound, all of those galaxies are probably going to merge with each other. And as a result, the black holes at their cores are going to merge with each other. So instead of just having a few black holes with perhaps millions or billions of solar masses, we can imagine that some black holes will grow to the size of trillions of solar masses. But even black holes, even the very large black holes, are not eternal. Black holes evaporate, providing that you wait for a really, really, really long time, which is why the red rectangle is now moving inevitably over to the right-hand side of the screen. So why do black holes evaporate? Well, Quantum mechanics, which has been with us for 100 years now, and as far as we can tell is a very good explanation of how things behave. Quantum mechanics allows particles and antiparticles to be created from borrowed energy. In other words, you can borrow energy from nothing and you can make an electron and an anti-electron, its partner if you like, which has all the same properties except opposite charge. And you can borrow energy and make a quark and an antiquark, or this particle and its antiparticle, in essentially any combination you like. But what happens after you've made the particle and the antiparticle is that they annihilate with each other and pay back the borrowed energy. In other words, we can borrow energy, make a particle and antiparticle, they annihilate and pay back the loan again. Let's just see that again. We can borrow energy from nothing, make stuff, and then pay back the loan when the particle and antiparticle annihilate. How does that help us understand what black holes are doing? Well, some years ago, Hawking said, well, I wonder what would happen if this process occurs just outside the event horizon. So let's imagine that's the event horizon of a black hole. What happens if we borrow some energy, make a particle and antiparticle, one of them falls into the black hole, but the other one doesn't? Now they can't annihilate. It looks like there's a net flux of something coming out of the black hole. We now call that Hawking radiation. It's a conjecture. It's a hypothesis. We can't measure what's going on because no black holes produce enough Hawking radiation for us to actually measure it. But most scientists concur that this process is occurring for black holes and will dominate the evaporation of black holes on large timescales. The radiation increases as the black hole gets smaller. So very large black holes will produce very weak Hawking radiation. But as they get smaller and smaller and smaller, the radiation gets more and more and more intense. So a black hole evaporates with larger and larger radiation levels until it finally disappears in a flash of radiation. And even the most massive, even the supermassive black holes, even those with trillions of solar masses, the ones lurking at what's left of the galaxies, even they will evaporate eventually, though it will take many trillions of times longer than small black holes that are, for instance, stellar mass. And so you see our red rectangle has now got to the extreme end of the screen. We can jump a little bit and say, well, what's going to happen on a timescale of 10 to the power 100? It's a nice round number. That's a googol. Not that googol, that's a misspelling of the actual number 10 to the power 100, which is a googol. On a timescale of 10 to the power 100, it has been calculated that every last black hole will have evaporated and there will be nothing in the universe left except radiation. There will be electromagnetic waves floating around the universe, but there will be no matter whatsoever. So after this particular point, nothing happens. In other words, time becomes essentially meaningless. You can argue that the universe will continue to expand and the radiation gets more and more and more dilute, otherwise known as the heat death of the universe. But essentially, it looks like nothing interesting will happen because there's no matter left in the universe. And we don't normally do this, but just to remind you how ridiculous a number is, like 10 to the power 100, let's write it out in full. There it is. 10,000 million. You can do it yourself. It's a very, very big number. But just because we as humans find it essentially impossible to imagine how big a number that is, or how long a time that is, one googol years, that doesn't stop us doing the calculations. It doesn't stop us applying the laws of physics as we understand them and say black holes will evaporate by the time we get to 10 to the power 100 years into the future. So it's not strictly speaking the end of time, but you could argue it's close enough. As Woody Allen said, eternity is a very long time, especially towards the end. But my favourite quote, I think, is from XKCD, who try and put a human spin on the universe. They say that a human is a system for converting dust billions of years ago into dust billions of years from now via a roundabout process which involves checking email a lot. I thought that's a very wonderful way of summarizing the human condition. So I told you about the end of everything, but so as not to leave you thoroughly depressed that everything is going to come to an end, let me finish with a slightly more upbeat epilogue. You could say that we live in a golden age. The sun is middle-aged and stable and well-behaved. And the moon is at just the right distance to stabilise the Earth's axis and hence stabilise the Earth's seasons. And as a bonus, it's also at just the right distance to give us the spectacle of a total eclipse of the sun as seen from the Earth's surface. And thanks to evolution, we are able to explore and discover and ultimately, hopefully, understand the universe in which we live. And we're able to do this because we can, for instance, build spacecraft, which we can send out into the solar system to visit our closest neighbours, to get a better idea of how the universe is put together. And we're able to build other devices, such as, for instance, telescopes, which allow us to see galaxies, perhaps billions of galaxies, at distances of billions of light years. But we could not have done this in the early universe. We needed generation after generation after generation of stars to process the hydrogen that was made in the very early universe into helium, and then process the helium into carbon and nitrogen and oxygen and calcium and phosphorus and iron, and all of the elements that we need to make us us. And as we've seen, if we think about the future, trillions of years from now, the universe is going to be dark and the universe is going to be boring. So you could say the best time to exist is now. Thank you all for listening.